During the previous A to Z presentations, we missed two important points, which are how to measure performance of this code ported to the FPGA, and even more interesting, where we are going to improve performance and how to optimize them. Let's use the Hello World code to see on a very simple example how we can tune it. As for software, we first need to identify where the time is spent, then look to the specific points we could modify or optimize. Then we can try to optimize the code. So HLS will be good at three specific points: loops, math functions, and parallel processing. So first of all, let's measure how long this hardware action takes. Let's look to the hardware action code using the Vivado HLS tool. So go to Action Hello World hardware, look if the KU060 directory has been created. If not, just do a make and you will get it. And then call Vivado HLS tool. Just open the project, go into hardware, select the KU060 without opening it, and type OK. This will open the entire project and give you some clues. Let's first identify all the Snap hardware settings that have been put by the Snap scripts. Go into Solution Settings, and you will see the different parameters. Go into Synthesis, and you will see here the 4 for 4 nanoseconds. This is the clock period we have set, and this is the part of the FPGA we have chosen. The other parameters that you may need to understand is go into project settings, and you will have in simulation the different path we have set, and in simulation, in synthesis, exactly the same thing, the different path we have set. These are all the paths where we need to find the header files. Let's now look to the code. In this example, we will consider only the hardware action. Open the source and the action uppercase.cpp file and look to the code. And notice that you have plenty of Pragmas, all commented except in the HLS action function. You can find two types of Pragma, the HLS unroll and the HLS pipeline. These Pragma are instructions that we can give to the HLS tool to compile the code differently. Now, let's keep that as it is, and let's try to find how much time this function is going to take. In the Synthesis tab, you will find two important information. One is the estimated clock. Remember that we have target at 4 nanoseconds the clock, and HLS for this design has estimated 3.5 clock. The second important information is about the logic used by the HLS Hello World action. In this example, you see that we are taking less than 2% of the FPGA. This is something important because it depends on the FPGA you have chosen. The third point where you can find data are in the Analysis tab. When you open, you see the different functions you are calling, and beneath you can even find the different loops that have been that are in your code. And you will see that the different names of the loops gives you the number of cycles taken by the loop. In this example, 64 by 2 is 128. If you add all the different loops, you get the total number for the main loop, which is 468 by 4 nanoseconds. This means that you have a main loop taking nearly 2 microseconds. Now that we have measured the time spent by the code, let's analyze it and see where we can optimize it. As we already spoke about it, let's identify the different paths of improvements, looking to loops, math function and code that can be parallelized. Just to show you multiple ways to use this tool, we can get these informations from the Synthesis tab. Go down to Performance Estimates, Latency, Detail and Loop, and you'll get details on time spent in loops. You may need to enter this instance to get these numbers. Here, no math or logic function, nor parallelism, since the example is far too simple. But keep in mind that HLS is really good synthesizing big amount of math and building quick and very efficient logic. Parallelism in code is very important. Imagine that you have a function which calculates a checksum and accumulates the result with an XOR. Then this code can be parallelized easily since the result is not used as an entry and the code can be so run in parallel with no problem. To guide the compiler to be efficient, we are going to drive him and check the result. An important point to notice here, I'm sure you have seen that at the bottom of the hardware action, we have coded a test bench. We never spoke about it until now, but this will be key to ensure that adding a Pragma will not break your code. After inserting a Pragma, just run this test bench. In a couple of seconds, you know if you broke something or not. So here is the list of optimization Pragmas that can be used. I took that from the HLS user guide UG902, which will be very useful for reference. You can just Google it to find it. We will not go through all of these Pragmas. The highlighted one will be used to solve some specific cases. 2 of them will be described just to let you understand what's behind these concepts to use them easily, the unroll and the pipeline. Once more, refer to UG902 to understand more about them. Also remind you that you shall always test your code first without Pragma and run test after Pragma insertion to ensure nothing is broken. Good to know also, adding a Pragma may reorder all the generated RTL files, such as you don't recognize your variable in debug mode. Unrolling is just flattening all loops so that they are all executed in one clock period. This means also that logic is duplicated n times if n loops, so potentially taking more space in the FPGA. You can add a factor to control the unrolling. Apply this unroll directive as soon as you see parallelization. About the syntax, there is no underscore before or after HLS in the Pragma call, and a Pragma is inserted in code just after the bracket of the loop or at the beginning of a function. Depending on its location, it will not have the same effect. A pipeline directive will first flatten the design, meaning unrolling loops, then look to the relationship between all variables and find which processing can be done before the end of another processing to understand what can be parallelized or pipelined. In this example, the compiler with this pipeline instruction will understand that the next RD read can be done during the com of the previous data. There is no reason to wait for completion of the full sequence. The initiation interval, also named II, which is the time between 2 reads, will so be reduced from 3 to 1 in this case. The overall latency will so be reduced also from 8 to 4 cycles. Pipeline is a recursive function, so handle it with care since it may add you a huge amount of logic for not better latency. pipeline can be very good for math processing. If it's not, then it can be due to the way your code is written. Now, let's look to the effects of applying these two simple pragmas. After measuring the time spent by the code in the first section and having understood some leverages to optimize this time, let's apply these pragma directives and see the effect. Let's see first the effect of unrolling loops. On top left, I will keep the measurement we found with no pragmas so that we can compare the effect of our optimization attempt. Let's uncomment the pragma unroll from the two cast functions on line 36 and 49. Save the file, run simulate to see that code is still okay, and run synthesis. Now look to the three main numbers. Clock frequency is okay, amount of FF logic, whatever it can mean, has increased significantly, and latency of main loop has decreased a bit. From 468 cycles, we are now at 338, so 1.3 microsecond. Let's go ahead and try and do it better. Second try, adding unrolling pragma in the uppercase loop, line 93. Save, simulate, synthesize, and look to the results. Clock frequency is unchanged, amount of logic is much better, and latency of the main loop is now 16. Wow, 16 cycles means main loop done in 60 nanoseconds. Looking closer to the cast loops, we see that they now have a latency of 0, which is expected. Indeed, a cast is just two different ways of reading the same data. So, reason to spend time with logic is just connecting bits differently. Can we do better? Third try, let's replace the unroll pragma line 93 by a pipeline pragma in the uppercase loop. Save the file and run synthesis. Clock frequency is unchanged, amount of FF logic has increased, and latency is worst. Bad idea. So let's try something else and forget about this example. Let's replace the pipeline by an unroll instruction. Fourth try, let's now uncomment the unroll pragma line 75 in main loop. Save the file and run synthesis. Clock frequency is unchanged, amount of FF logic is quite unchanged and even a little better than the second try. And we get back this latency of 16. What I wanted to show you here is that with very few instructions well placed, so you can get really good performances. If you do more tests, you will see that this pipeline instruction has overwritten all the unroll that you have put in subloops. Remember, pipeline is a recursive instruction and has entered all the subfunctions to get a better latency. Let's come back on parallelism at a higher level of your code. A function returning a checksum, for example, is something that is not ordered, has no relationship. HLS tool will show you that you have succeeded parallelizing your function if you see in your synthesis results the following. Duplication of the code, and here is a picture on the right of an FPGA where HLS has been able to duplicate 30 times the same algorithm. This means that the process can be done 32 times faster. This helps us beating CPU and even GPU in some cases. Important, you may need to help the HLS compiler by recoding your loop so that you break the relationship and help HLS to build parallelization. Conclusion, test your code before and after applying a pragma. Take time to build a short test case exercising the hardware action. This may save you time to debug if you have an issue. As you have seen, the location and the type of the pragma can really optimize your code greatly. It may be worth spending time to save some. UG902 will be your reference. Just Google it to get the last version. And at last, look carefully to the log of the HLS synthesis. Most of the information you find in analysis are displayed here. That's all for this part. I hope this will have given the basis to give a huge acceleration to your offloaded code.